sklearncrossdecompositionPLSSVD. Description: partial least squares with singular value decomposition PLSSVD is a dimensionality reduction technique that aims to find latent variables that explain the maximum covariance between two data matrices, X and Y. It's a powerful tool for analyzing data where variables are highly correlated or where the goal is to identify common patterns in both datasets. Inputs: X, a matrix of predictor variables, n samples. N features X. Each row represents a sample, and each column represents a predictor variable. Y, a matrix of response variables, n samples. N features Y. Each row represents a sample, and each column represents a response variable. Outputs: X scores the scores of the X data projected onto the latent variables. This represents the variations of X explained by the model. N samples, N components. Y scores the scores of the Y data projected onto the latent variables. This represents the variations of Y explained by the model. N samples, N components. X loadings, the weights for each predictor variable in the X data that contribute to the latent variables. N features X. N components. Y loadings, the weights for each response variable in the Y data that contribute to the latent variables. N features Y. N components. Steps. Step 1: compute the covariance matrix between the X and Y data. Step 2: perform singular value decomposition SVD on the covariance matrix. Step 3: extract the top component's latent variables based on the singular values, which capture the maximum covariance between X and Y. Step 4: project the X and Y data onto the latent variables to obtain the scores and loadings. Metrics: R2X, the proportion of variance explained in the X data by the model. R2Y, the proportion of variance explained in the Y data by the model. Visualization plots. sklearncrossdecompositionplot, a plot showing the singular values, which helps identify the optimal number of components to retain. Scores plot, a scatter plot of the X scores and Y scores, visualizing the relationship between the X and Y data in the lower dimensional space of the latent variables. Loadings plot, bar plots of the X loadings and Y loadings, revealing the importance of each feature in contributing to the latent variables. Fine-tune parameters. N components, the number of latent variables to extract. This parameter controls the dimensionality reduction. Scale, whether to scale the X and Y data before performing PLSSVD. Scaling can improve the performance if the variables have different scales. Algorithm. The algorithm used for SVD can be RPAC for large matrices or SVD for smaller matrices. Uncertainty methods. Bootstrapping, repeatedly sampling the data with replacement and performing PLSSVD on each bootstrap sample to estimate the variability of the model parameters. Cross-validation, splitting the data into training and validation sets, and using the validation set to evaluate the model's performance. Challenges and fixes. Challenge 1: overfitting. The model may overfit the data if too many components are selected or if the data is noisy. Sample use case that resulted in challenge 1: a model with too many components might perfectly fit the training data but fails to generalize well to new data. Fixes to challenge 1: use cross-validation to select the optimal number of components. Regularize the model using techniques like L1 or L2 regularization. Use a simpler model with fewer components. Challenge 2: collinearity. Highly correlated variables in the X data can lead to instability in a model. Sample use case that resulted in challenge 2: when multiple predictor variables are highly correlated. The model might become sensitive to small changes in the data, leading to unstable results. Fixes to challenge 2. Perform feature selection to remove highly correlated variables. Use regularization techniques to penalize large weights for highly correlated variables. Consider using other dimensionality reduction techniques such as principal component analysis (PCA) before applying PLSSVD.